All right, good morning. We're going to go ahead and get started. So, as I said, we're going to do exam 2 review first, and then we'll get around to chapter 5. Just out of curiosity, how many of you were able to take a look at the exam 2 review? I know you may not have had a chance because of all the chapter 4 homework. Okay. So I pulled some questions from there that usually have questions associated with them or are a little bit more difficult. So we're going to do those, and then we'll go over chapter 5. I'm going to post the exam 2 review answer key after this class. I just didn't want to post it until we went over it and talked about some of the questions. Here's your first question. How many neutrons are in the nucleus of an atom of cobalt 60? And remember, you're going to need a periodic table for this. I'll give you 2 minutes to do this problem. Okay, so it looks like the folks you have put an answer out said B. Let's see how to solve this. This 60 here, what is that? What does it mean? We're looking at an isotope, that's right, and the 60 is the mass number. And the mass number is equal to the number of protons plus the number of neutrons. Where do you get the number of protons from? You get it from the periodic table. It's the atomic number on the periodic table. And in this case, cobalt, the periodic table says that it has an atomic number of 27. So 60 is equal to 27 plus the number of neutrons. If you subtract 27 from both sides, then you should get 33. So the answer is B. How do we feel about that one? All right. Starting off a little easy because I know it's very early in the morning. Now here's a chapter 3 question. Which of the following properties of gasoline is a chemical property? A, B, C, D, or none of the above? Oh, so there's a question. So when there's an isotope, is it always going to have an altered mass number? So generally, yes. So if you have an isotope, that means that you have an atom that has a certain number of protons, but it doesn't have an equal number of neutrons. All right, so most of us are saying, or it looks like everyone who's chiming in is saying E, none of the above. Let's go through and identify these. So colorless liquid, color, that's something physical, so we don't even care. Density, That's also physical. Boiling point, again, physical. And they're all properties. So the answer is E, none of the above. Hopefully exam 2 will not be that bad. I'm going through and starting to grade exam 1, so you will get those grades back soon. But exam 2 is going to be primarily multiple choice. Just given the topics that we've covered, it's hard to do, anything else. So if these questions are fairly easy to you, then exam 2 should be a pretty easy time. Questions about chemical properties, physical properties, chemical changes, physical changes, because that's what this question is relating to. If not, you can tell me that you're good. All right. Here's one of the slightly more difficult questions. This is calculating an atomic mass. So I will give you 3 minutes, and then I'll check back in with you. I see that we have a couple of answers here. Do we still need some more time? Okay. I'll give you another minute. In the interest of time, we're going to keep going here. I'm going to start solving the problem, but if you're not done yet, just keep going and put your answer in. So like I said, this is a atomic mass question, which means that you have to calculate a weighted average. I like to make a table so that I can have all the information I need to calculate these things. So for each of these isotopes, we're going to need to know the percent abundance and their atomic mass. Isotope X63 has an atomic mass of 62.940 AMU. And X65 has 64.928 AMU. And we're given the abundance for X63. We don't have an abundance for X65. What do we have to do here? Exactly right. You have to subtract the percent abundance that you have from 100, because your total should always be 100%. Let me try to write this a little bit better. So you should get 30.83% abundance for the X65 isotope. When we convert these to a decimal, all you're doing is taking this decimal point and moving it over, to the left twice. It's the same thing as dividing by 100. Is everybody with me so far? All right. Now we just have to set up our actual calculation. So we're going to multiply the decimal times the atomic mass and add that to the decimal times the atomic mass. And I'll write out what that looks like. So that first part is the contribution from X63. Now the second part that's the contribution from the second isotope X65. When you do that, you should get 63.55 AMU, which is A. Now here's another way that you can at least rule out some answers. The two atomic masses for the two isotopes are 62.9 something and 64.9 something. You can't have an atomic mass that's greater than either of those numbers. It also can't be less. So D and E are not options, and you should immediately get rid of them. The only ones that make sense are A, B, and C. Does everyone see that? How you could eliminate D and E because those answers are too large. Your weighted average has to come somewhere between the averages that you, or the masses that you already have. So when you're doing a multiple choice test, the best thing you can do is eliminate answers first. Unless you know it cold, eliminate answers. That way you can't choose the wrong one. How do we feel about this problem? Great. Great, great, great. So there's another one like this on the exam review. And again, I will post the answer key after this class. So you'll be able to check your work and ask questions. All right. Which atom has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10? You will absolutely need a periodic table. Again, periodic table is your friend. You're going to need it for the rest of this course. So whenever you sign on for class, have a periodic table. I'll give you a couple of minutes and then I'll check back in. If you've already gotten the answer, then I also want you to write out the electron configuration for tin. So that's a hint if you haven't figured it out. It's not tin, it's not D. So write out the electron configuration for tin, and that's just going to be more practice for you. So for this question, I agree. It's letter B. So you have to know your periodic table. And for the exam, you can recreate a periodic table that has the information on it that you want. So remember how we went through for chapter 4 and we wrote all over that thing in terms of all the different, the S block and P block and D block, and which main energy level each thing was. You need to get comfortable with that. If you're comfortable with that, then you'll be able to follow along each of these pieces until you land on the correct element. And it seems like, let's see how many, 3. So about 7 of you put in an answer that was correct. So hopefully everyone else is on the same page. Do we have a question about how we got to letter B as the answer? Okay. So now I'm going to write out the configuration for tin, which I asked you to do just as practice. I'm not going to ask you to put that in the chat because it would be a nightmare. So just check it against your own. Before I go any further, looking at your periodic table, what's the last sub-level that I should be filling for tin? Which, if you can't find it, it's SN is the symbol. What is the last sub-level? I'll specify in the question, India, whether or not I want you to use the long form or the noble gas form. We're going to cover the noble gas form today. So for your test, it's only 3 and 4. So it will not be noble gas configuration. Chapter 5 has the noble gas configuration, and that's where you could be asked both. But yes, it should be in the P block, right? So that means that our last sublevel is going to have something to do with a P. So that's what you should have gotten for your electron configuration. Are there any other questions regarding electron configurations? Again, it's something that you need to practice. Alrighty, then we'll move right along. Now we've got 2 questions up because they're fairly short. This first question is a conservation of mass question, which we covered, I believe it was more in the YouTube lecture. We didn't do a specific problem for chapter 3 when we were doing the live lecture. So again, remember, the live lecture is not a substitute for what's put on YouTube because we don't have time to cover every single concept. But between the homework, quiz, chapter check-in, and exam review, everything will be covered that's talked about in the lecture posted on YouTube. So go ahead and do both of these questions, and then we'll go over them. Do we have an answer for the first question about the limestone? Or are we stuck? You can say help if you need some help. Yeah, you don't have to sit there and be like, well, I'm going to just stew in it and wait. Yeah. So conservation of mass. Just to quickly review that, in terms of chemical reactions, the mass of the reactants is going to be equal to the mass of the products. Because you can't create or destroy matter. So with that little bit of information, does that make more sense? So take another minute and give it a shot. Let's write out what the reaction is. So the reactants, there's really only one thing. It's limestone. It's decomposing by heat. So the only reactant is limestone. We're creating calcium oxide, which you will not need to know how to write out these chemical formulas yet. But in chapter 6, which is coming, you will. So we have calcium oxide and carbon dioxide gas. And the question is asking us about the mass of the limestone. Well, we know the mass of the calcium oxide and the carbon dioxide. So if we add those together, it should equal the mass of the limestone. When you do that, you get 10.11 grams. Does everybody follow that? Now, what if I said that you have 12.7 grams of limestone and you create writing this and making it up at the same time. So we have 12.7 grams of limestone. You create 9.3 grams of calcium oxide. How much carbon dioxide do you make? So this is a separate question. Still a conservation of mass question. But what would we have to do here to figure out how much carbon dioxide we make? Yes, you have to subtract. So you would take 12.7 and subtract 9.3. And you should get 3.4 grams. Those are the only two variants of that question that you can have. It'll be here are all of the products and the masses of those. What's the mass of the reactants? We'll only have one thing to figure out. It's not going to be, well, there's two reactants and here's the mass of the products. You can't do that yet. So if this makes sense to you, you're golden for conservation of mass. Do we have an answer for the second question about the number of carbon atoms in vegetable oil? Let me know if you need more time. I'll give you another minute, see if we can get some other folks chiming in with their answer too. And don't be ashamed to say help, because that lets me know. Yeah. Help is participation too. All right. So we have a combination of help and 57. So let's see. We have to figure out how many carbon atoms there are. Carbon, its symbol is C. So we're looking for the number of C's in this molecule. These subscripts, these tell you the number of each atom. So anywhere you see the letter C with a subscript, that tells you that you have some carbons. If you don't see a subscript, then you assume that there's one. So let's go through and circle all the carbons. There's a carbon there, there, and there. We've also got these parentheses, which I'm going to make bigger, with this 3 here. What this means is it's just like math. Everything that's inside the parentheses, you multiply by 3. So to get the total number of carbons, we're going to take our 3 carbons from here. So I'm going to try to color code this so that one's black. We've got our 17 carbons here. And then we also have this 1 carbon here. So this shows you where each carbon is. And you have to multiply what's in the parentheses by 3 because there's a 3 here. So it's 3 plus 18 times 3. And that should give you 57 carbon atoms. So for those of you who said help, does this make sense now? Let's do one more practice for you guys who said help, just to make sure you got it. Now I want to know the number of hydrogens. I'll give you a minute. I want you to calculate the number of hydrogens in this molecule. I like what I see. So we've got the 5 on the outside, and then we've got 33 hydrogens inside of those parentheses. So we have to multiply those by 3. And your answer should be 104 hydrogen atoms. So the only tricky thing here is when you see the parentheses and there's a number on the outside. You can't forget to multiply. And also sometimes you'll see kind of loners like that carbon out there. So it's just paying attention to detail. That's it for the exam review. We're now ready to move on to chapter 5 stuff. So are there any questions regarding exam 2? Because it's this week. I know we just had an exam and now we have another one. There's going to be an exam for every 2 chapters. So this coming exam is on chapters 3 and 4. Exam 3 will be on chapters 5 and 6. Exam 4 will be on 7 and 8. And then your final exam will pretty much be an exam on chapters 9 and 10, plus questions from all the previous chapters. So it's going to be like taking 2 exams in one. And just like before, you'll have a 3-day period to take it. You will not be required to upload your work this time because there really isn't much in the way of math. It's not like the the metric conversions and things like that we were doing in chapter 2. So you get it right or you get it wrong. But it's really hard to do partial credit with conceptual questions. So this will be a primarily multiple choice exam. So is everybody clear on that? Wednesday through Friday, take the exam. It'll be open, and that's it. So if you have questions about that, let me know. Also, while I'm thinking about it, I posted an announcement because I tallied up across all my classes when office hours will be. And what came out as the winner is Wednesdays from 2 to 4 p.m. So we'll still use the same way to link up to office hours, but this is the official time. If that does not work for your schedule, then you can always send me a message through course messages and set up an individual time. It looks like there might be a question. Can you guys still hear me? Raise your hand if you can hear me. Okay, cool. Thank you. Alrighty. So let's move on to chapter 5. I'm sure that most of you have not had a chance to look it over due to the homework and there's an exam coming. So I will move forward like you haven't really looked at it. I'm not going to cover everything that the YouTube lecture covers. So you will still need to watch that and make sure. Okay, so there's a question. When writing down the laws, do we need to remember the person associated with the specified law? Not really. I may use the name in the question, so that will help you. But I'm not going to ask you to write down the person or the year. I'm not worried about those details. I want to make sure that you get the concept. So what is the law and what does it mean? Fair? No problem. So going forward, that's what I'm looking for. I'm not necessarily looking for you to remember people's names. If you do chemistry as a major, there are certain names that you will simply know. But if you're like in business management, you don't need to remember Niels Bohr. Like that's just, you don't have to take up your brain space on that. It's totally fine. Other questions, or are we ready to start chapter 5? Well, let's roll. Chapter 5. So there's more history to the development of the periodic table. I talk about more of that in the YouTube video. So again, this is an abbreviated version. Ooh, struggle. An abbreviated version so that we can get to some of the major concepts and go over those. The history lesson, that's not really a concept. It's just me telling you about things. And okay, you need to know this vocabulary word or this law means this. So I'm not going to spend time on that. I am, however, going to talk about Mendeleev because he is known as the father of the modern periodic table. there were prior proposals on how to organize all of these elements as they were being discovered. And all of this was happening at the same time that people are talking about, okay, what is matter made of? So you have the development of all of these models of the atom, what the structure of the atom is like, how electrons, once they're discovered, how are electrons being arranged in an atom. So all of this stuff is going on at the same time. It's not like, okay, we figured out that atoms have this structure. Now let's talk about the periodic table. It's all happening at the same time. So Mendeleev proposed that chemical elements will repeat their properties in regular intervals when they're arranged according to increasing atomic mass. And so he made a periodic table in columns based on the formula of the element's oxide. So that means forming a compound with oxygen. And he said that all of the elements that form a compound with one oxygen will be in one column, with two oxygens in this column. And so that's how he organized his periodic table. I'm not going to show you what that looks like. Again, that's in the YouTube video. But just know that he's the father of the modern periodic table. Now, he didn't know about noble gases. And there were other elements that he didn't know about that he was able to predict, but not noble gases. So that periodic table was expanded to include noble gases once argon was discovered. They said, oh, whoa, hey, there's a whole nother group that we didn't even know about. And they were initially called inert gases because it was thought that they wouldn't do any chemistry at all. It turns out that some of the heavier ones like xenon and krypton, you can do some chemistry with them. But for the most part, they don't really want to be bothered. H.G.J. Moseley was the one who added in that final piece to create the periodic table that we know today. So you will need to know the periodic law, which I will define on the next page. So Moseley said that, hey, maybe instead of atomic mass, we should look at the nuclear charge. And nuclear charge means we're looking at the number of protons. How many are there, right? If you increase by 1 for each element, then the trends on the periodic table, which we're going to discuss in chapter 5, are actually better behaved. So instead of atomic mass, like Mendeleev suggested, they're going on atomic number. And that's periodic law, that the properties of elements recur in a repeating pattern when arranged according to increasing atomic number. So you will need to know this. And that concept, combined with the energy levels from Bohr, which hopefully you remember that name from chapter 4, those two things combined to give us the periodic table that we know today. So that's your little bit of chemistry history lesson. Again, those are concepts and knowing, it's like a history test. It's really difficult to test you on that outside of a multiple choice question. I'm not going to have you write an essay on this. It's a 100 level course. And I'm going to be real, I don't want to read all those essays. So for chapter 5, it's going to be multiple choice as well, some of it, when we get to exam 3. But are we good so far in terms of understanding what you need to know for chapter 5 for the history lesson? Good. So make sure you check out the lecture video that's posted on YouTube because it goes more into detail. There are a few terms and things that I did not include. Go ahead. What's your question? if there is a question. Or not. It's okay. So now we're going to talk about the periodic table. We talked about it some in chapter 4. We're going to talk about it more in this chapter. The first thing is to give you some more lingo. The way that the periodic table is organized, there are vertical columns and there are horizontal rows. The columns are called groups, and those groups have chemical properties, and they follow trends with physical properties. The periods are the rows. All the elements in a period, they show a range of properties. There are no patterns in terms of that. But what we are concerned with is the groups. The way that I remember which is which is this mnemonic. The group is the column that goes up and down, and the period goes across. So you'll need to know those two terms. This is a periodic table that doesn't have any numbers on it really. But what it does have is lots of common names for groups, and for we're looking at the numbering system for those groups. And you will need to know the information on this page. Now, I don't have a slide for each individual common name and group, but I have that in the YouTube lecture. So I'm going to give you the overview so that you understand what you need to know, but go to the YouTube lecture for the nitty-gritty details. We clear on that? Thank you. I was like, I can wait you out. I have toddlers. I can wait forever. Okay. The first thing that I'll go through is the group names. All of the groups don't have common names, but there are 4 that you need to know, and I will mark them. So everything with an asterisk is a common group name. You will sometimes see a group referred to as a family. I usually don't use that terminology, but you may see that in your textbook. They use both. So group 1A is the alkali metals. They're pretty highly reactive. Group 2A is the alkaline earth metals. 7A is the halogens. In 8A, you have noble gases. Now you'll notice that there are just plain old numbers, and then there's numbers with Roman numerals, and they have numbers with letters. So you might see it as a Roman numeral, or you might see it as just the number with a letter. The A for each group means that it is a representative element. And what we're talking about is the S block and P block elements. Then there are the B elements. Those are the transition elements. So I will highlight which is which. In red, boxed in red, those are our representative elements. Green, these are the transition elements. And those are the D block elements. The F block elements, which are down below, are called inner transition elements. And they're broken up into two groups, the lanthanides and the actinides. I would highly recommend printing out this specific slide for your notebook. You could also recreate it if you wanted to, like print out the periodic table that I provide for you on Blackboard and then write all of these things in. Whichever one makes the most sense to you, whichever helps you the most with understanding and remembering this terminology. But you will need to know these terms, not just to regurgitate them, but to understand what the question is asking. Because I could ask you, which of these elements is a transition element? And I'd give you 5 choices, and you have to choose one that would be in the group that I circled in green. So does that make sense for how you're going to need to understand all these terms? Okay, so make sure that you know this slide. Now we're going to talk about periodic trends. When you're going over the YouTube lecture, I recommend having a couple of periodic tables that are blank so that you can write in trends and so that you can write in whatever other information about the periodic table on the periodic table. It can help you study, and you can refer to those for your homework for mastering chemistry and chapter check-ins and stuff like that. The first periodic trend that we're going to talk about is atomic radius. You may also see it referred to as atomic size. On a periodic table, as you go up a group and left to right on a period, your radius is going to decrease. So this is our first trend. As you go up a group, so from the very bottom of a group to the top, you're going to have big to small. And then in reference to left to right, big to small. Let's see what that really means. So here's some representations of atomic radius. The transition elements are not included here because there's a lot of exceptions. So we're really only talking about the representative elements. This cesium atom is much bigger than lithium. But, let me do a different color here. If you compare lithium to fluorine, lithium is bigger. So it's all relative. Does that make sense? We're talking about relative sizes. So the types of questions that you might see would be, okay, which element is the smallest? And I'd give you a list. Which element is the biggest? So that's the type of question you'll see here. Now the explanation for why, let's talk about it. We said that for energy levels, the bigger the energy level, the further away electrons can be from the nucleus. So if you're at n equals 5, your electrons can be much further away than n equals 1. So that means at n equals 5, you're going to have a bigger radius than at n equals 1. So that one should already kind of make sense because we talked about it in chapter 4, even though we didn't exactly identify it as a periodic trend. However, going across a period, we did not cover. As you add more protons, which is what you're doing as you're going across the periodic table, you're adding protons, but you are not adding energy levels. So, as you go across the periodic table, you're adding protons, you're adding electrons, but you're not making the size of your atom any bigger. The number of energy levels and sublevels is already set. And the protons are able to draw those electrons in a little bit closer the more that you add in. I talk about that in detail in the YouTube video, so make sure that you check that out. This is just giving you the overview. So if between this and the YouTube video you still don't get it, let me know. But it may not all sink in right now because you're hearing it fresh at 9 o'clock in the morning. But you will need to know, again, the trends for atomic radius. As you go up and across, you decrease. The second trend we're going to cover is metallic character. So what that means is how easily will an element give up an electron from its outermost energy level. The metallic character trend is the same trend as atomic radius. As you go up a group and across a period, it will decrease. So elements over here have very little metallic character, which makes sense because on the far right of the periodic table, you have nonmetals. Is everybody with me so far? We just covered 2 trends of the periodic table. Okay. We're going to cover one more concept and then we'll take a quick break. Along with the trends on the periodic table, just by looking at it, you can say, oh, okay, this atomic radius is smaller or bigger than this one. You can also predict physical properties. So here's a table that has group 1A elements. And listed, I've got the radius, density, melting point, and atomic mass. You can already see the trend. Cesium is the biggest radius, right? And sodium is the smallest so far. I have blanked out what's there for lithium on purpose. In terms of density, overall, you're going from a smaller density to a bigger density. Now, that trend does not necessarily hold, but for this particular group, it does. There's a little bit of fluctuation here with sodium and potassium, but that's normal. Overall, you see a trend of the lighter element has a smaller density, bigger element, bigger density. We see a trend here for melting point where it's decreasing, and the atomic mass is increasing. If I were to ask you, based on the information that we have here, what would you guess the density is for lithium? Do you think it's going to be bigger than 0.97 or smaller than 0.97? It should be smaller because that's what the trend is. And if I gave you more information, like if I gave you actual numbers, you should be able to pick it out from multiple choice question, knowing that the density of lithium should be smaller than the density for sodium. What about the melting point for lithium? Do you think that it's going to be bigger or smaller than 97.8? It should be bigger because that's what our trend is. We're decreasing as we go down the group. So that means anything that's above sodium should have a larger or a higher melting point. In atomic mass, we're increasing as we go down. So that means that the mass should be smaller than 22.99. So that's the kind of reasoning that you're going to have to be able to do when it comes to physical properties. It's not something that you necessarily know or memorize, but you understand how to figure it out. So are we clear on that? You guys did pretty well with guessing, so at least those of you who are participating in the chat, I know that you got it. But please, 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 if it doesn't make sense to you, don't just sit on your hands. You can say, wait a minute, or help, or anything like that. Related to, I had a question for you. All right, so let's do this. I forgot. We're going to do chemical properties too, and then we'll take a break. So predict the density of barium given the density of calcium and strontium. And I put the order of these from the periodic table. So this is the group that you have to work with, just in case you don't have a periodic table on you. But you're given information for calcium and strontium, and you're asked about barium. So take a second and figure out which one of these makes sense. Put your answer in the chat. Okay. So, multiple choice questions. Always try to rule out answers. We see that calcium has a density of 1.54 grams per cubic meter or centimeter, and strontium is 2.63. So that means that our trend is increasing as you go down the group. So our answer has to be bigger than 2.63. We can rule out A, B, and C. Now you've got a 50-50 shot. Since there are numbers here, what you can do is figure out the difference between the calcium density and the strontium density. So this is the difference between the two. So that means the difference between strontium and barium should be 1.09. So if you add whoops, gave you the answer. So it should be 2.63 plus 1.09. And you get D. So a little bit of math there. But just by understanding the concept, you can whittle it down to two answers and take a guess. So how do we feel about that type of problem? That's about as complicated as it gets. I could have also said, here's the density for calcium, and here's the density for barium, and you tell me what strontium is. So that's the other variation there. Okay. So just like physical properties, you can predict chemical properties too. And Mendeleev actually arranged his periodic table according to the formula of the oxide. So all of the elements in group 1A have the same formula, M2O. So the M is whatever element. So lithium, sodium, potassium. This is the same general chemical formula for that whole group. So if I tell you that the formula for the chloride of calcium is CaCl2, what do you think the formula for the chloride of barium is? You have to look at your periodic table and see whether or not they're in the same group. Now, from the problem that we just did, we know that they are. So since they're in the same group, what do you think the chemical formula is for the chloride of barium? It should be very similar to calcium chloride. So are we good on that? Or do we have questions? So this is a good time for a break. We will break until 9:30. Then we'll come back and finish up chapter 5. So I'll see you in about 10 minutes. All right, so we're back. And I see a question in the chat. would all other elements in group 2 have Cl2 at the end? Yes. So that's the whole idea here. Everything in this same group will have the same formula. So the last part of the class, we're going to spend with electron configurations and ionic charges. So please make sure that you have a periodic table. We're going to start with just writing the electron configuration for manganese. So I'll give you a couple of minutes. You don't need to put your answer in the chat because putting an electron configuration in there, not exactly easy. But just make sure you do it in your notes and then I'll go over it. We're going to write out the full configuration and then I'll show you how to write the noble gas configuration. Are we ready for me to start writing it out or do we need a little more time? Well, let's get started. I always say start at the beginning. It's a good place. I'm going to throw these labels up here just for reference. So if you weren't able to get that electron configuration, hopefully these labels will help you. So our full configuration starts with 1s2. We go down to the second row because we have not hit manganese yet. We fill the 2s with 2 electrons. Then we fill the 2p with 6 electrons. We're still not at manganese, so we keep going. We fill the 3s, followed by the 3p. We're still not at manganese, so we have to go down to the fourth row. 4s, we fill it. Now we're in the neighborhood of manganese because it is in the 3D. So we count 1, 2, 3, 4, 5. And 3D5 is the last part of our full configuration. So just by a show of hands, or you can say me, how many people were able to write that full configuration correctly? So if you were not, that's okay. And you can always say, not me. Maybe it was because you didn't have enough time, and that's fine. But if it's because you didn't understand it, you need to let me know. So you can always send me a private message through the chat. You can talk to me after class directly, or you can send me a message through course messages. We can do office hours. So don't just sit in it and stew. Make sure you get the help that you need. So that's the full configuration. We did that in chapter 4. Should be review, especially since you have an exam Wednesday through Friday. You got to take it. If you watched the other video that I posted on electron configurations, you would have already been introduced to what's called the condensed or the noble gas electron configuration. So instead of writing out this super long string, you can write something much simpler. Manganese is in period 4. For the noble gas electron configuration, we're going to look at the noble gas in the period above our element. So the noble gas in period 3. That would be argon. If we were to write the full configuration for argon, it would be 1s2, 2s2, 2p6, 3s2, 3p6. All of this. Instead of writing that, you can write argon, just the symbol for it, in brackets. And that's implying everything that I just underlined. Now you need to fill in the gap between argon and manganese. So we still need to write some portion of a configuration, but a much smaller part. The only thing that's left is what's in period 4. The 4s2 and 3d5. That's the noble gas configuration. Again, this is chapter 5. So you will not see the noble gas configuration on the exam this week, but it will be on exam 3. So how do we feel about that? So let's try an example. I want you to write both the full and the noble gas configuration for selenium. I'll give you a couple of minutes and then I'll check back in. I want the full configuration and the noble gas configuration for selenium. Are we ready or do we need more time? All right, let's go. So selenium is in the same period as manganese by design, so that if you didn't understand, you could at least have kind of a jumping point since we just did manganese. So I'm not going to write out all of the 1s, 2s, and all that on this one. But if you still feel like you need that or you need some help figuring that out, let me know. So that's what you should get for your full configuration. Manganese, we stopped at 3D5. Selenium, we finished this 3D. So that's 3D10. And then we got onto the P block with 1, 2, 3, 4. For the noble gas configuration, what noble gas did you use? Right. It should be argon because it's in the same exact row as manganese. So it's the same core, but we have to add on everything between argon and selenium. So if all of this, that's our core, then that means all of this is the extra. And that's what we need to write here. So that's the noble gas configuration. And I'm sure you're probably like, really, Dr. Hefner, how come we couldn't do that in the first place? Because you wouldn't really know what that meant, the argon in brackets. You got to understand where it comes from. Know your history. So how do we feel about, okay, so why are we using argon? Because argon is the noble gas that is in the row above where selenium is. So you always go for, so selenium is in period 4. You have to use the noble gas in the period directly above the element. So that means you need to go to period 3. Does that answer your question? Yes. If we were writing one for sulfur, then you would use neon. Now keep in mind, we're doing this for neutral atoms. Atoms are not always neutral. They can't be if we're going to form chemical formulas. The electrons that are involved in doing chemistry are called the valence electrons. So if you remember, which I hope you do because it was just on this last slide, that was our configuration for selenium. The valence electrons are the electrons in the outermost principal energy level of an atom. They are the S and P electrons that are beyond the noble gas core. So in this case, our noble gas core would be argon. We're not really thinking about the 3D, okay? There can be some chemistry there, but what we're really talking about is the valence electrons in the S and P. Now, I'm not going to be as tricky and give you like a transition element or anything like that, but this is full. The 3D is full. We're looking at the electrons in the S and the P sublevels for valence electrons. One more thing on valence electrons. Almost forgot. So you know that group number that we've been talking about? The ones with the A behind them, those are the representative elements. And the number tells you the number of valence electrons. So in group 1A, all of those elements have 1 valence electron. Group 2A, they all have 2 valence electrons. If we were to be in group 6A, there would be 6 valence electrons. So you don't even really have to think about it. You just have to know what the group number is, as long as we're talking about a representative element that has the letter A behind the number. So is that clear for valence electrons? We're talking about the ones that are the furthest out. They're involved in chemistry, And you can get that just from the group number, as long as the group number has the letter A at the end of it. Is that clear? Good. So if I asked you, how many electrons does a group 5A element have, what would your answer be for a group 5A element? Yeah, there would be 5 valence electrons. Good, good. We can represent those valence electrons using an electron dot formula, or it's also called a Lewis dot structure, which is what it was called when I was going through this. We can just call it a generic electron dot formula. Either way, same thing. You visually represent the valence electrons of an element. So you write the symbol, and then you write dots going around the element to represent how many valence electrons there are. We said for group 5A that there's going to be 5 valence electrons. One example of a 5A element would be phosphorus. Its symbol is a P. There's 4 sides that we can use, but we have 5 valence electrons. First thing you're going to want to do is go around and fill each one of those sides. We don't want to pair up electrons unless we have to. And since we have more than 4 electrons, we're going to have to. So that is the Lewis dot structure for phosphorus. Now, the second one that I drew is wrong. And the reason is you don't pair electrons unless you have to. This whole side is open. Electrons don't like to hang out next to each other unless they're forced to. They have the same charge. Electrons are all negative. So they don't want to be hanging out in the same orbital unless they're forced to. Does that concept make sense? So the example that I give in the video about this is if you've ever had family come over and you got cousins from out of town and y'all around the same age, if you don't have no guest bedroom, which growing up I did not, the guest bedroom was my room. And I just happened to be there too. So you got family coming in from Georgia, Virginia, wherever else. I'm from New Jersey, so that's a little bit of a drive. You're sharing your bed. Twin size bed, doesn't matter. Head to foot, foot to head. Okay? You are sharing that bed. You are not happy about it, but you're sharing. Now, I have an older brother. He had to share too, only if we had boy cousins. On my mom's side, ain't no boy cousins. So we was all sharing. He was comfortable. I had to share. I was not happy. Your feet stink after 12 hours in the car, so wash them. Anyway, that's what I think about when I think about pairing electrons. Don't put them together unless you have to. And wash your feet. Those are the 2 lessons that you should get from here, all right? So let's move on. Our final trend is ionization energy. Ionization energy is talking about the amount of energy that it takes to remove an electron in the gaseous state. In general, ionization energy increases as you go from the bottom of a group to the top and from left to right. So again, when you're going through the lecture on YouTube, make sure that you have this trend on your periodic table. The other two were atomic radius and metallic character. Those two have the same trend, decrease, decrease. Ionization energy is different. It increases and increases. So this is just showing you what that looks like. And we can actually rationalize why ionization energy increases as you go up a group or across the periodic table. Very briefly, if you think about how far away the electrons are, the electrons are much closer to the nucleus the higher up you are in the group. So the closer to the top you are, the more of a hold the nucleus has on its electrons. So you're going to need more energy to strip them away. Likewise, when you're going across the periodic table, you're increasing the number of protons, but you're not changing the number of energy sublevels. So those protons are holding on to those electrons more tightly. So you need more energy to strip it away. The other way that you can think about it is metallic character talks about how easy it is to lose an electron. And if you're a non-metal, like these elements over here, you're not going to have very much metallic character if you're a non-metal. So that means that you're going to have low metallic character and a higher ionization energy. Again, I go over it in the YouTube video. So if your brain is starting to overload, it's okay. If it doesn't make sense between this and the YouTube lecture, let me know. The last concept that we're going to cover is ionic charges. And this is setting us up for chapter 6, where we talk about chemical formulas with naming and writing chemical formulas. So if you do not understand ionic charges, chapter 6 will be the struggle bus. So make sure that you understand this concept before next week. When we're talking about charges, we've got two options, positive and negative. We'll start with the easier ones first, positive ions. Most of the periodic table consists of metals. Metals, when they're involved in chemistry, they react by losing their valence electrons to form positive ions. So notice I have the capitalization and the bold and all the things for you to remember. Metals lose, and they are always positive ions. So if we have sodium and its electron configuration, the valence electrons are going to be the ones in the outermost principal energy level. That's going to be the electron that's in the 3s orbital. If we lose that one, because metals lose electrons, we now have an imbalance. Look at your periodic table. What is the atomic number for sodium? It's 11. Right. So that means that you have 11 protons, and in a neutral atom, you also have 11 electrons. If we lose one electron, we still have 11 protons, but we now have 10 electrons. So we have more positive charge than negative charge. So our sodium has a +1 charge. That's what that superscript is there, the positive sign. So if it's anything other than +1, you're going to see a number there. So if it was a 2, you'd see 2 plus, 3 plus, 5 plus, okay? But sodium is just 1, so you can just write a plus sign. Does that concept make sense? We lost an electron. Now there's an imbalance of charge, because that's the key to all of this. Let me know if I need to go back over that. I got one yes. I need to know if there are other people who feel the same way. Do we get this concept? Thank you. So in general, for a metal, the ionic charge is equal to the group number. And we're talking about the representative elements, so the ones that have the A behind them. So group 1A, all of those have +1 charge. Group 2A, +2 charge. Now remember, we're talking about all the metals. So as you go further to the right, you're getting closer and closer to the non-metals. So don't just go through assuming, oh, okay, I can just take the group number and that's the charge. Make sure that you're talking about a metal from the representative elements. So all the ones that have the A behind them. So let's do an example together. The first thing I want to do is figure out the charge for a magnesium ion. Look at this portion of the periodic table, find magnesium, and tell me what you think the charge is going to be. We're doing positive charges, so it has to be positive, right? But what's the number? Right. The magnesium ion should have a 2+ charge. And without even doing anything with the electron configuration, you should be able to figure that out from the group number. So on this one, I don't have the group numbers. But if you have your own periodic table, you can see that pretty clearly. So that part's easy. Done. Writing the electron configuration, though, let's do that. We're going to do the full configuration, and then we'll do the noble gas configuration. I want to do this to demonstrate a point. Then from here on out, we're just going to do the noble gas. So let's start with a neutral atom of magnesium. That electron configuration, if you walk across the periodic table, you do 1s2, 2s2, 2p6, 3s2. We said that magnesium is going to form a positive ion, so that means it's going to lose some electrons. What electrons are we going to lose? 1s, 2s, 2p, or 3s? Exactly, we're going to lose the 3s. Why? Because these are the valence electrons. So we're going to lose those 2 electrons. When we write out our configuration for the ion, we're just not going to include the valence electrons. So that is the electron configuration for the for the magnesium ion. How would I write the neutral magnesium ion configuration? It's not an ion, it's an atom. Let's try that again. How would I write the neutral atom magnesium electron configuration using noble gas configuration? So we're in period 3. Which noble gas am I going to use to represent the core of the magnesium atom? Yeah, we're going to use neon because it's in the one above. So all of this, everything up through 2p6, is neon. Then we just write out what's left between neon and magnesium, and that's 3s2. If we lose those 2 electrons, that is our configuration. It looks like neon. How do we feel about that? And it's okay if you're like, meh, because we're just introducing it. I know most of you probably did not have a chance to look at the lecture that was posted. But do you think that you could maybe do something like this if you were kind of walked through it again? Okay. So you'll definitely want to practice this, okay? Based on time, I'm gonna keep going to negative ions because negative ions are a little bit trickier. And then we can kind of go backwards if we have some time and do another example. So positive charges, we were talking about metals. Negative charges are for negative ions, and we're talking about nonmetals. So the far right side of the periodic table, excluding the noble gases. Nonmetals will gain electrons. And we're talking about groups 5A through 7A. Those are the nonmetals that we're talking about here. If you were to go through and write the electron configuration for an atom of oxygen, this is what it would be: 1s2, 2s2, 2p4. Since it's going to gain electrons, the only place we can put those electrons is in the p. We can hold a maximum of 6, and nonmetals want to gain electrons to complete that energy level. So we've added 2 electrons to complete oxygen. And now it has a charge of -2. If you look at the periodic table, you can see that the atomic number for oxygen is 8. So that means that the neutral atom has 8 protons and 8 electrons. When we add those 2 electrons, we still have the same number of protons, but now we have 10 electrons. So this means that we're going to have a negative charge. And the difference between the electrons and the protons is 2. We've got more electrons than protons. So that's what our charge is going to be. Are you with me so far? In general, to determine the ionic charge of a nonmetal that's a representative element, so again, 5A through 7A, you're going to take the group number, so we'll use the one for oxygen. Oxygen is in group 6, 6A. You're going to take that number, the 6, and subtract 8. That gives you a -2. So that means that all 6A elements have a -2 charge as ions. So that's a fast way to figure it out. So if I told you that I want you to figure out what the charge of a group 7A element would be, how would you do that? If you were making an ion with a 7A element, what would its charge be? You take the group number 7, subtract 8, and you get -1. So metals and nonmetals, 2 totally different things. Let's do the same kind of example that we did for the positive ions, only with the negative ion. We're going to look at sulfur. Sulfur is beneath oxygen. It is still in the group 6A. So its ion is going to have a -2 charge. That part is done. The electron configuration, though, that's the trickier part. I'm going to use the noble gas configurations here. We're going to look to neon because that is the noble gas in the period above sulfur. So for the neutral atom, We're going to start with that neon core, and then we're going to write everything between it and sulfur. So we've got 3s2, and then we've got the 3p, 1, 2, 3, 4. Now we have a negative charge here, so that means that we are adding electrons. The charge tells you how many electrons you're adding. We're going to add on 2 electrons. The only place that you can add those is in the p orbital. So don't add any electrons to the s orbital, please. It will make me cry. So this is the ion, where we've got 2 extra electrons. In terms of noble gas configuration, well, this is a complete octet. There's 8 electrons here. So if we were to rewrite this in proper noble gas configuration, we'd be adding 2 electrons, which means that we're going 2 places to the right. We're adding 2 electrons. So it actually looks like argon. The negative ions are adding electrons, so they are going to look like the noble gas in their period. It would be the same thing for phosphorus. Phosphorus looks like argon when it has gained electrons. Talk to me if you have questions, or if you're just like, this is a question mark for me, Dr. Hefner. Struggle. We got a question mark. The negative ions are always the tougher ones to do. So let's do another example. I just said phosphorus is going to look like argon. So let's do phosphorus. Phosphorus is in the 5A. So to figure out its charge, we're going to take 5 minus 3. Or 5 minus 8 to give us negative 3 for phosphorus. Is that part clear about how we come up with the charge for the ion? Okay. The electron configuration, though, that's the part. So if we were going to do it for a neutral atom, we would again have that same neon core because it's right next to sulfur. The only difference is it's got 1 less electron, okay? So does that part make sense? We're just writing out the noble gas configuration for a neutral atom of phosphorus. Now this is the important part because I got to figure out where you're getting lost. I have my guesses, but I need confirmation, so thank you. Since we are forming a negative ion, are we going to gain electrons or lose electrons? We're going to gain. That's right. How many electrons are we going to gain? Good. So you're with me up to that part. The only place we can put more electrons is the P sublevel because it's not full yet. So if we carry over what we wrote and just add 3 electrons, instead of having 3p3, it's 3p6. Do you follow? Because I know this next part is probably where we got lost. So do you understand that? Good. All right. What we did was add enough electrons to phosphorus so that we completed the level 3 energy level, okay? So there are no more spaces available in main energy level 3. Full. S is full, P is full. We're not even worried about the 3D right now because that doesn't fill up yet. What element has this configuration where everything is full up to the 3s and the 3p? The noble gas, argon. It's in the 3rd row, right? So it's the 3rd period, which means that all of its s and p orbitals are full. So what this really looks like is argon. Does that jump make sense? Does it at least make more sense than it did? Because we're just going for improvement at this point. Okay. So let's check your understanding. Without writing out any configurations, let's look at arsenic. It's in the same group as phosphorus, just in a different period. So when we form an ion with arsenic, if we form a negative ion, what noble gas is it going to look like? The configuration for the ion. Yes. It's going to look like krypton. So if you understand that, then you understand the concept of doing the negative ionic charges. So we've got about 8 minutes left. Would you prefer to do another example for positive ions or negative ions? Because we've only got enough time for one, and we won't really have time for doing reminders. So if we do another example, we can't talk about reminders, which I don't have a slide for reminders because I forgot, ironically. But there are a couple. So put your vote in the chat. Reminders, positive ions, negative ions. So the question that I see is, the end result for the negative ions should look like the corresponding noble gas. Yes. For negative ions, the goal is to fill up that orbital and look like the noble gas. We're split. Okay. So we'll do a little bit of both. Quick reminders. Exam 2 this week, Wednesday through Friday, starts at 8 a.m. Wednesday, ends 11:59 p.m. Eastern Time on Friday. Primarily multiple choice. You will not have to worry about uploading your work. Just do the exam. You have Chapter 5 work to do for Mastering Chemistry. Just do that. I'm not going to give you a chapter check-in for this week. The exam plus Mastering Chemistry is enough. Next week, we're starting chapter 6. If you do not understand ionic charges by then, it's going to be a struggle. So make sure that you do. Office hours this week, everyone voted. 2 to 4 on Wednesdays, set in stone. You need something outside of that, message me. Now for another example. Fluorine. It's in group 7A. What charge is a fluorine ion going to have? Right. You have to take 7 and subtract 8. So it's going to be -1. You can just put a minus sign, okay? So that's the fluorine ion. What is the noble gas configuration going to be for fluorine? It's going to look like neon. Because we're adding 1 electron, and that's going to complete the 2p. That's all that I have for you. Oh, isoelectronic series. We're not going to have time to go over that in full detail. But we'll talk about it again. We'll talk about it the beginning of next week as part of the Do Now. Make sure that you watch the video. So this is talking about atoms and ions with the same electronic configuration. So for example, the fluorine ion and neon are isoelectronic. They have the same number of electrons. And I go through and do an example in the YouTube video that shows you, I think I talked about potassium and phosphorus being isoelectronic with argon. But if you understand the concept of the positive and negative ions, the isoelectronic series should be easier to you. And that's all I have. So if you have any questions or anything like that, let me know now. If you want to stay after until, people have signed off and then ask a question, that's fine too. So if you're good, you're free to go.